afternoon, everyone. Thank you for joining me today. So, today we embark on a journey to understand the fundamental language of electromagnetism, or the Maxwell's equations. These four elegant equations, conceived by James Clerk Maxwell, revolutionized our understanding of electricity, magnetism, and light, paving the way for modern technologies like radio, TVs, and even our beloved smartphones. So, let's begin with the first equation. It is the Gauss's law for electricity. So, imagine a closed surface, like a balloon. This law states that the total amount of electric flux, so think of it as electric field lines, passing through that surface is directly proportional to the net electric charge enclosed within. In simpler terms, it tells us the relationship between the source of electric fields, electric charges, and their strength. So, mo na ang formula. So, please do. Nasa screen mo na ang formula. Next equation is the Gauss's law for magnetism. Now, let's move on to the magnetism. Unlike electricity, magnetic monopoles, it is isolated north or south poles, haven't been observed. This is beautifully captured by Gauss's law for magnetism. So this law states that the total magnetic flux, think of magnetic field lines, passing through a closed surface is always zero. So in simpler terms, there are no isolated magnetic poles and magnetic field lines, always formed closed loops. So, mao na diya ang ikaduha nga formula. Next is the Faraday's law of induction. This is the third equation. So imagine a magnet moving near a coil of wire. This movement induces an electric current in the wire. So this phenomenon is explained by Faraday's law of induction. This law states that a changing magnetic field induces an electric field, and the magnitude of the induced electric field is proportional to the rate of change of the magnetic field. In essence, it tells us how a changing magnetic field creates an electric field. So that is the third Maxwell equation, the Faraday's law of induction. Now to our last equation, we have the Ampere's law. Ampere's law originally stated that a steady electric current produces a magnetic field. However, Maxwell realized something profound. A changing electric field itself can also generate a magnetic field. So this crucial addition to Ampere's law, known as Maxwell's addition, is the final piece of the puzzle. It completes the picture by showing that not only currents but also changing electric fields can create magnetic fields. So that's it for the fourth equation. Now that we all have four equations, the magic happens. By solving these equations together, we discover that changing electric and magnetic fields can propagate a self-sustaining wave, an electromagnetic wave. So this wave encompasses the entire spectrum of light, from radio waves to visible light to gamma rays. So Maxwell's equations not only unified electricity and magnetism, but also predicted the existence of light as an electromagnetic phenomenon. So, in conclusion, Maxwell's equations are the cornerstone
This
of
topic is all
classical
about the
electromagnetic
electromagnetic
physics.
waves.
These four
Electromagnetic
element
waves are also
equations not
known as
only
EM waves.
explain everyday phenomena,
Electromagnetic radiations are composed of
but
electromagnetic waves
also
that are produced
lay the
when an electric
foundation for
field
many modern
comes in contact
technologies,
with a
from
magnetic
the
field.
glow of your phone screen to the radio waves carrying
The
music in
Maxwell
the
equation,
vacuum of air.
electromagnetic waves
Maxwell's
prediction and
equations are the sonic
observations.
symphony orchestrating the world around us.
The Scotsman James Clerk Maxwell
Today,
on
thank
1831 to
you for listening.
1879 is regarded as the greatest theoretical physicist of the 19th century. Although he died young, Maxwell not only formulated a complete electromagnetic theory represented by Maxwell equations, he also developed the kinetic theory of gases and made significant contribution to the understanding of color visions and the nature of Saturn rings. Maxwell's complete and symmetric theory showed um, that electric and magnetic force are not separate, but different manifestations of the same thing, the electromagnetic force. This classical unifications of force is one motivations for current attempts to unify the four basic forces in nature, the gravitational, electrical, strong, and weak nuclear force. The waves predicted by Maxwell would consist of oscillating um, electric and magnetic field, defined to be an electromagnetic waves or EM waves. Electromagnetic waves would be capable of exerting forces on charges great distance from their source, and they might thus be detectable. Maxwell calculated that electromagnetic waves would propagate at a speed given by the equations. So, muna siyang equations. C is equal 1 all over square root of mu 0 times the epsilon 0. So, ang kana C is stand for the speed of electromagnetic waves. So, ang value sa kanang mu 0 is equal to 8.85 times 10 raised to the power of negative 12. Then, sa kanang epsilon is 4 pi times 10 raised to the power of 7. So, if imo na siya calculate, um, ang answer niya is 3.00 times 10 raised to the power of 8 meter per second. So, mo ni siya nga tuwang speed of the light sa electromagnetic waves. So, next is the Hertz observations. So, the German physicist Heinrich Hertz on 1857 to 1894 was the first to generate and detect certain types of electromagnetic waves in the laboratory. Starting in 1887, he performed a series of experiments that not only confirmed the existence of electromagnetic waves but also verified that they travel at the speed of light. Hertz used an AC RLC or resistors inductor capacitors circuits that resonate at a known frequency and connected it to a loop of wire. High voltage induced across the gap in the loop produced spark that were visible evidence of the current in the circuit and that helped generate electromagnetic waves. Across the laboratory, Hertz and another loops attached to another RLC circuits which could be tuned to the same resonance frequency as the first and could thus be made to receive electromagnetic waves. This loop also had a gap across which spark were generated giving solid evidence that electromagnetic waves had been received. So, the apparatus used by Hertz in 1887 to generate and detect electromagnetic waves, an RLC circuit connected to the first loop goes spark across the gap in the wire loop and generate electromagnetic waves. Spark across the gap in the second loops located across the laboratory gave evidence that the waves has been received. Hertz also studied the refraction, and interference pattern of the electromagnetic waves he generate, verifying their wave character. He was able to determine the wavelength from the interference pattern, and knowing the frequency, he could calculate the propagation speed using the equation. Hertz also studied the refraction, and interference pattern of the electromagnetic waves he generated, verifying the wave character. He was able to determine wavelength from the interference patterns, and knowing their frequency, he could calculate the propagation speed using the equations. Velocity is equal the frequency times the wavelength. So Hertz was thus able to prove that electromagnetic waves travel at the speed of light. The SI unit for frequency is the hertz. His name is his honor.
Production of electromagnetic waves. The current in the antenna produces the circular magnetic field lines. The current produces the separation of charge along the wire, which in turn creates the electric field as shown. The electric and magnetic field near the wire are perpendicular. The magnetic field varies with the current and propagates away from the antenna at the speed of light. It means that when there is a current flowing through an antenna, it generates a magnetic field with circular force around it. The direction of the magnetic field lines is determined by the direction of the current flowing through the antenna. The current flowing through the wire causes a separation of electric charge along the wire. This separation of charge creates an electric field around the wire. The electric field is perpendicular to the magnetic field. The magnetic field strength changes as the current flowing through the antenna changes. Additionally, the magnetic field propagates or spreads out from the antenna at the speed of light. This means that any changes in the current will cause corresponding changes in the magnetic field, and these changes will propagate away from the antenna at the speed of light. Receiving electromagnetic waves. Electromagnetic waves carry energy away from their source, similar to a sound wave carrying energy away from a standing wave on a guitar string. An antenna for receiving electromagnetic signals works in reverse. Unlike antennas that produce electromagnetic waves, receiver antennas are specially designed to resonate at particular frequencies. An incoming electromagnetic wave accelerates electrons in the antenna, setting up a standing wave. If the radio or TV is switched on, electrical components pick up and amplify the signal formed by the accelerating electrons. The signal is then converted to audio and video format. Sometimes big receiver dishes are used to focus the signal onto an antenna. In fact, charges radiate whenever they are accelerated. When designing circuits, we often assume that energy does not quickly escape AC circuits, and mostly this is true. A broadcast antenna is specially designed to enhance the rate of electromagnetic radiation, and shielding is necessary to keep the radiation close to zero. Some similar phenomena are based on the production of electromagnetic waves by varying currents. So, electromagnetic waves carry energy from their source, and the receiving antenna works by capturing this energy. When an electromagnetic wave hits the antenna, it accelerates electrons, creating a standing wave within the antenna. By this standing wave is then converted into an electrical signal that can be amplified and transformed into audio or video output by the receiver, such as TV or radio. Big receiver dishes can focus incoming waves onto the antenna to enhance signal strength. Electromagnetic radiation occurs whenever charges are accelerated, which is a fundamental principle in designing both transmitting and receiving antennas. In everyday devices, shielding is used to prevent unintended radiation, ensuring energy remains within the circuit. Relating electric field and magnetic fields. There is a relationship between the electric and magnetic field strengths in an electromagnetic wave. This can be understood by again considering the antenna just described. The stronger the electric field created by the separation of charge, the greater the current, and hence the greater the magnetic field created. Since current is directly proportional to voltage or Ohm's law, and voltage is directly proportional to electric field strength, The two should be directly proportional. It can be shown that the magnitudes of the field do have a constant ratio equal to the speed of light. That is, E over P equals to C, or electric over magnetic equals to speed of light. Is the ratio of the electric field strength to magnetic field strength in any electromagnetic wave. This is true at all times and at all locations in space, a simple and elegant result. So, in an electromagnetic wave, the electrical field and magnetic field are directly proportional to each other, and the ratio is always equal to speed of light. This relationship can be understood by considering the behavior of an antenna. A stronger electric field caused by a separation of charge leads to a greater current, which in turn produces a stronger magnetic field. Since current is directly proportional to voltage or Ohm's law, and voltage is directly proportional to the electric field strength, the electric and magnetic fields in an electromagnetic wave are proportional to each other. So mathematically, this relationship is expressed as electric over magnetic field strength equals the speed of light, where c is the speed of light. This constant ratio holds true at all times and in all locations in space, reflecting a fundamental analytical property of electromagnetic. So these are the formula on how to find the speed of light, the electric field strength, and even the magnetic field strength.
So moving on to our next topic, which is the electromagnetic spectrum. So the electromagnetic spectrum is a range of frequencies or energies of electromagnetic radiation, including all forms of radiation that can be emitted or transmitted by electromagnetic waves. This spectrum spans from very low frequencies to very high frequencies. Electromagnetic or electromagnetism is one of the branch of physics. It has a range of all types of electromagnetic radiation, and electromagnetic spectrum is the entire distribution of electromagnetic radiation according to their frequency and wavelength. So here is the types of electromagnetic radiations. So first is the radio waves, which are used for communication, broadcasting, and navigation. Second is the microwaves, used for heating, communication, and radar applications. Third is the infrared radiation, is used for heating, thermal imaging, and night vision. Fourth is the visible light, so the most visible part of the spectrum, including the Roy-G-Biv colors, which is the red, orange, yellow, blue, violet. So here is the relation of wavelength, frequency to energy of a photon. So first is ila-ilahon usa nato ang wavelength, ang frequency, of course the energy. So wavelength is the distance between consecutive peaks or troughs of an electromagnetic wave. Frequency is the number of oscillations or cycles per second of an electromagnetic wave, while the energy is the amount of energy carried by an electromagnetic wave. So when the wavelength is increases, the frequency is decreases and the energy is decreases. So when the wavelength is decreases, the frequency and the energy increases. So that's the relationship of wavelength and a frequency to energy of a photon. So mao ni ang wavelength equation. So the C there is a speed of light, which is equivalent of 3.00 times 10 to the power of 8 meter per second. While ang kanang Y nga murag nabali is gitawag na siya og wavelength. The V is the frequency. So let's have a problem solving. so that nga atong mahibaw-an og unsaon pagkuha ang unsaon pag-calculate ang wavelength. Okay. So let's begin the problem solving. Number 1 is, what is the wavelength of a wave having a frequency of 3.76 times 10 to the power of 14 s negative 1. So our formula is C equals wavelength and frequency. So ang speed of light, which is the C, is equivalent na siya is 3.00 times 10 to the power of 8 meter per second. So i-substitute na to ang sa C, and then atong gipangita is ang wavelength. Let's substitute also the frequency, 3.76 times 10 to the power of 14 s negative 1. So by dividing the two equations, so ato makuha ang atong answer, which is a 7.98 times 10 negative 7 m, which is the wavelength. So that's the final answer. Okay, number 2. What is the frequency of a 6.9 times 10 to the power of 13 m wave? So maora gihapon atong i-substitute atong C, 3.00 times 10 to the power of 8. So kay frequency man atong gipangita, so given na ang wavelength, which is a 6.9 times 10 to the power of negative 13 m, which is the wavelength. So by dividing the two equations, ato makuha ang answer, which mo ang 4.35 times 10 to the power of 20 s negative 1. That's our final answer. So number 3, what is the wavelength of a 2.99 hertz wave? So substitute the C, the speed of light, which 3.00 times 10 to the power of negative 8 to the power of 8 meter per second. So the wavelength is 2.99 hertz, and ang answer na to, i-divide ang duha with mo ang 1.00 times 10 to the power of 8 m, which is the wavelength. So number 4, what is the frequency of a 7.43 times 10 to the power of 5 m wave? So maora gihapon, let's substitute the speed of light, 3.00 times 10 to the power of 8 meter per second, and a frequency, mao ang wavelength, ang 7.43 times 10 to the power of 5 m. So ato makuha ang frequency, 4.04 times 10 to the power of 12 s negative 1. So that's our final answer. So sayo na kaayo siya, i-divide na to og i-substitute ra na to, og ato nang ilailahon nga mao na ang frequency or mao na ang wavelength. So ing ana ra ang paag. Radio and TV waves are forms of electromagnetic radiation which are used to transmit information through the air or space. They are a type of non-ionizing radiation, meaning they do not have enough energy to break chemical bonds or cause harm to living tissues. So radio waves are a type of electromagnetic wave that has frequency range. They are used to transmit information through radio communications systems such as amplitude modulation, frequency modulation, shortwave radio, cellular networks. And the TV waves, also known as broadcast television, are type of electromagnetic wave that has frequency range, and they are used to transmit television programs through the air or via satellite.
So, microwaves. A microwave oven, or simply microwave, is an electric oven that heats and cooks food by exposing it to electromagnetic radiation in the microwave frequency range. This includes polar molecules in the food to rotate and produce thermal energy in a process known as dielectric heating. So, electromagnetic waves with wavelengths longer than those of visible light but shorter than those of radio waves. They are often used for cooking food, in radar, and for communication technologies like Wi-Fi and cell phones. So next is infrared. Infrared waves or infrared light are part of the electromagnetic spectrum. People encounter infrared waves every day. The human eye cannot see it, but humans can detect it as heat. These waves have longer wavelengths than visible light, but shorter than microwaves. They are emitted by objects due to their temperature and are commonly used in night vision devices, remote controls, and heat sensing. Next is visible light. The visible light spectrum is the segment of the electromagnetic spectrum that the human eye can view. More simply, this range of wavelengths is called visible light. Typically, the human eye can detect wavelengths from 380 to 700 nanometers. So, the portion of the electromagnetic spectrum that is visible to the human eye, consists of different colors with wavelengths ranging from about 400 to 700 nanometers. It's essential for sight and is used in various lighting applications. Next is ultraviolet or UV light. Is electromagnetic radiation of wavelengths of 10 to 400 nanometers, shorter than that of visible light but longer than X-rays. So, electromagnetic radiation with shorter wavelengths than visible light but longer than X-rays. UV light is responsible for causing sunburn and tanning but also has applications in sterilization and some medical treatments. Next is X-rays, or a form of electromagnetic radiation similar to radio waves, microwaves, visible light, and gamma rays. So X-rays is high-energy electromagnetic waves with wavelengths shorter than ultraviolet light but longer than gamma rays. So X-rays are commonly used in medicine for diagnostic imaging such as X-ray radiography and computed tomography or CT scan. So, familiar naman ta ning X-ray, di ba kay mo ba ni kasagaran nato nga ikuan nang natay like sa medical, mo ba na need nato. Next is the last but not the least. I mean, gamma ray. A gamma ray is electromagnetic radiation of the shortest wavelength and highest energy. Gamma ray, the most energetic form of electromagnetic radiation, with the shortest wavelengths and highest frequencies. Gamma rays are emitted by radioactive materials and nuclear reactions. They have applications in cancer treatment or radiotherapy and in various types of imaging, including nuclear medicine. So, that's it.
So, kibaw naman taon sa mga different types sa electromagnetic waves. So, here, let me ask you, if these all are electromagnetic waves, then why are they different from each other? Well, the answer is very simple. It is because of wavelength and frequency. We know that there is inverse relationship between them. If you increase the frequency, wavelength decreases and vice versa. Now, listen carefully. Radio waves are different from microwaves. It is because both the frequency and wavelength of radio waves are different from the microwaves. Similarly,
X-rays are different from gamma rays due to different frequency and wavelength. Therefore, electromagnetic waves are different from each other due to having different frequencies and wavelengths.
So our next topic for today is the speed of electromagnetic wave in a vacuum and matter. So what is an electromagnetic wave in a vacuum? An electromagnetic wave in a vacuum refers to a wave constructed of oscillating electric and magnetic fields. It propagates through space void of matter, which is what we refer to as a vacuum. For you to understand how fast the speed of electromagnetic waves travel in vacuum, imagine you have a flashlight. When you turn on the flashlight, it emits light, which is actually an electromagnetic wave. This wave travels from the flashlight to your eyes at the speed of about 300,000 km per second. This means that it can go around the Earth more than 7 times in just 1 second. To get the wave speed, we can use the formula wave speed equals wavelength times frequency, wherein the units of wave speed is meter per second, wavelength is meters, and frequency hertz. So we have here the 3 sets of problems. Number 1, a wave has frequency of 50 hertz and a wavelength of 10 meters. What is the speed of the wave? To solve this, we will first write the given. Frequency is equal to 50 hertz, wavelength is equal to 10 meters, and the unknown here is the wave speed. Using the formula, wave speed is equal to wavelength times frequency. Substituting the given, 10 meters times 50 hertz multiply is equal to 500. Since the unit of wave speed is equal to meter per second, we will write here 500 meter per second. Number 2. A wave has frequency of 5 Hz and a speed of 25 meter per second. What is the wavelength of the wave? First, we would write the given. Frequency is equal to 5 Hz. Wave speed is equal to 25 meter per second. And our unknown here is the wavelength. Using the formula, wave speed is equal to wavelength times frequency. We will manipulate the formula. We have the wavelength is equal to wave speed over frequency. Substituting the given, 25 meter per second, the wave speed, and the frequency, which is the 5 Hz. Divide is equal to 5, and since the unit of the wavelength is meters, we have here 5 meters. Number 3. A wavelength of 10 meters and a speed of 340 meter per second. What is the frequency of the wave? First, write the given. Wavelength is equal to 10 meters. Wave speed is 340 meter per second. And the frequency is unknown. The formula, wave speed is equal to wavelength times frequency. Manipulate it. We have frequency equals wave speed over wavelength. Substituting the given, we have 340 meter per second over 10 meters. Divide, we have 34. Since the unit of frequency is hertz, we have 34 hertz. Thank you. That's all.